Alright, so I'm going to go ahead and give you guys a bit of a review on some of the cofactors. I think that Mike did a pretty good job, but I think there's some things that we can maybe connect together here that will make this worth your time. So there's going to be a few things we're going to cover. Really, it's going to be TPP, PLP, biotin, and we'll touch NADPH just for one step. But really what I want us to focus on is what these things are doing and when you're going to use different cofactors. So I find that these cofactors are oftentimes the more difficult ones to remember, and they do interesting stuff, so that's why I chose to focus on them. So the first thing we'll go over is carboxylation, and carboxylation is going to use biotin. And then we have decarboxylation. So decarboxylation will use either TPP or PLP. It can also be spontaneous depending on what species you have. And then number 3, we're going to go into PLP transamination, and then maybe touch on how you can do an isomerization reaction with PLP. All right, so with that, we'll start off with biotin. So I've tried to draw some of this stuff out already to speed this video up. We'll see how it goes. So in order to talk about biotin, I figured we could talk about the biosynthesis of malonyl-CoA. So malonyl-CoA, if you've forgotten, is used in fatty acid and polyketide biosynthesis. Alright, so it's a really important extender unit, so we'll go over how that's made, and it's made using biotin. And it's an enzyme called acetyl-CoA carboxylase, shown here, which is a really interesting enzyme that actually is used as a target for pesticides in plants. So plants have actually two acetyl-CoA carboxylases, one in their plastids and one in their cytosol. And one of them is actually a good target for developing pesticides. And these are going to be molecules that don't attack the mammalian acetyl-CoA carboxylase. So in order for you to put on a carboxyl group, the first thing that you have to do is activate it. So the first step that I'm showing here is the activation step, and that's going to be done using ATP. So here's your ATP. And then what's going to happen is you'll have a molecule of bicarbonate here, and that will just attack one of these phosphate groups. So then you'll form what is called a carboxyphosphate. And for good measure, I'll go ahead and put my negative charge there. So this carboxyphosphate is an activated form of bicarbonate. Now it's activated, you can actually begin to use this carboxyl group and attach it different places. So once you've made the carboxyphosphate, the second thing is to transfer to biotin. Here is a not so pretty rendition of biotin, but biotin's a pretty interesting cofactor. It's got a little tail over here, and that's actually going to have a connection to a lysine inside of an enzyme. So in this case, you're going to use this top part of the ring here, and this nitrogen is actually going to attack this carboxyphosphate, and then you're going to kick out your phosphate, and then you're going to form this guy. So it's called carboxybiotin, so we'll go ahead and write that in, carboxy. Alright, so this is kind of your activated intermediate, or your activated second intermediate. So now you're ready to transfer it to the acceptor, and in this case, if it's malonyl-CoA carboxylase, you're going to have acetyl-CoA. That's going to be your acceptor. So you will deprotonate this alpha proton, essentially making an enolate ion that can then attack. And once you do that, basically this will end up kicking out. And you'll get this, which will end up resetting. Grab this conveniently placed proton, and then you'll of course get your product. In this case is going to be malonyl-CoA. And you can imagine that you're going to see the same reaction if you make methyl-malonyl-CoA. The only difference is that you'll have a methyl group here instead of having the methylene. So yeah, you could have this, same general process, same type of enzyme, and that's just basically going to use biotin to attach this carboxyl group. Alright, so that's biotin. So just remember, this requires energetic input. So ATP is used in order to activate your bicarbonate. So this is an uphill reaction, use energy. So that actually creates this, as we said, malonyl-CoA. So the decarboxylation of this is what drives forward carbon bond formation and polyketone fatty acid biosynthesis, because in order to reinstall this carboxyl group, you have to use ATP. Alright, so that's biotin. So that's carboxylation, but we'll go into decarboxylation now instead. And so decarboxylation depends on a couple things, and I'll do my best to go through them. But what you really want to ask yourself when you're talking about decarboxylation reactions is, what type of carboxylate do you have? Now, the first thing to consider is you have a beta-keto acid. Now, beta-keto acids, shown here, they're actually quite prone to decarboxylation. So yeah, here's an R group over here, right? So this is your carboxyl group. And so the way that you would number a carboxylic acid is the alpha position is the one that is next to the carbon that forms the carboxylic acid, the alpha position, and this is the beta position. So this is called a beta keto, because this is a ketone acid. It's a beta keto acid, and because of the positioning here in this beta keto acid, you can see that there's some favorable ways to undergo decarboxylation. So if you just add a little bit of heat, you know, this thing readily will decarboxylate. This is the classic way to kind of show this mechanism. This six-membered intermediate, this will collapse. You'll form an enolate ion here, which will then attack a proton, and then you'll get just your ketone. So this is your decarboxylation of beta keto acids. There are enzymes that do this, but this will also happen spontaneously on its own. So you can imagine that this is favorable, and the reason that this is favorable is because you have an electron sink here. So whenever you form CO2, these electrons will leave, and they don't just build up here. They can actually resonate into this system here, and that means that you have some kind of stability. So beta keto acids are not too hard to decarboxylate, but if you have an alpha keto acid, the question about how to decarboxylate it becomes a little more complex, because you can't do the same thing that you do with beta keto acids with alpha keto acids. And just to show you why it's an alpha keto acid, let's go ahead and say this is the carboxylic acid and this is the alpha position, and you can see that this is a ketone. So if you want to be able to get rid of this guy, you're going to need something a little better than what you have. So I'll show you. The problem with decarboxylating here is if you try to do what we did before, basically form your second bond to oxygen down here, right? Then you're going to need to break a bond. So you need to break this bond, and the electrons only really have one place to go, and that's onto this carbon here. And so what you end up forming is something like this over here. You get your CO2, and then you get a pretty unstable intermediate. So this guy right here is unstable. So you're going to have to think of a way, or at least in the sense of, you know, if you were a chemist, and maybe some of you are, but if you are a living organism, I suppose, you'll have to think of a way to make this an energetically favorable reaction. And so what we need here is an electron sink. And so for alpha keto acids, the way that you decarboxylate them, remember this is for alpha keto acids, so if you remember, how do I decarboxylate an alpha keto acid? TPP. So that's over here. So this is just an overview of TPP as a cofactor. I didn't feel like drawing it. So you can see there's some stuff over here, but we don't really care about that stuff. We really care about this thiazolium ring here in the middle. Alright, and this thiazolium ring has an acidic proton, and so you can actually deprotonate this, and these electrons will come back and hang out on this carbon and form what we call an ylide. So the ylide will be this stabilized carbon ion due to the fact that you have some nice aromaticity in this ring, and that can act as a stabilizing force for that negatively charged carbon. Alright, so in order to demonstrate TPP, we're going to talk about alcoholic fermentation. You also see TPP in a couple other places, so you'll see it in, I don't want to use green here, so other enzymes with TPP. So you'll have pyruvate, dehydrogenase. Let's write that a little bit better. Another one is alpha ketoglutarate, dehydrogenase, succinate, DH. And if you've taken metabolic biochemistry, you'll also know that the breakdown of a lot of these amino acids requires that you end up with a beta keto acid, which then will have special enzymes that are very much like these guys, but are specific for different substrates. So these are other places you'll see it. These are a little more complex. I would review these two. Maybe pyruvate dehydrogenase is a good one to consider. Mike usually asks a question for an enzyme mechanism from primary metabolism on the first test, so one of these different type of cofactor enzyme mechanisms might be something that you'll see. Alright, so for alcoholic fermentation, this is a situation where yeast have no oxygen, right? So this is an anaerobic process, so if you run out of oxygen you can't do oxidative phosphorylation, and so the end of glycolysis you form pyruvate, which is shown here, and in order for glycolysis to continue you have to restore NADH, and so NADH, which that reminds me, that's not NADPH, that is NADH. We'll fix that real quick before we go forward. NADH. Alright, we'll get down there in a second. Alright, so the process of glycolysis requires that you use NAD+, because you're oxidizing glucose in order to make energy and ATP, so you end up with pyruvate, and then if there's no oxygen to restore your electrons for your electron carriers, which is shown down here, basically NAD, then you have to restore them, and the way that you do that is fermentation. And so you'll take pyruvate, and then pyruvate will be decarboxylated, and then afterwards it will be reduced using NADH to reform NAD+. Alright, so in this enzyme you have your TPP, right? So this is TPP, and as I said, this is the active form, this is a thiazolium ring, and then you have the ylide, right? So you have a negative charge on this carbon, so this is going to be a good nucleophile, and so you're going to go ahead and attack the ketone of pyruvate. And if you're confused as to why it's the ketone, just remember the stability of things. You're not going to attack the carboxylate over here. This carboxylate is a more stable position in this molecule because you have resonance with these oxygens, while the ketone has no resonance, it just has the dipole, which means that it's the more likely one to be attacked. Also remember, this is an enzyme active site, so even if something happens that you don't understand, it's probably because the enzyme active site is set up to do that. Alright, so after this attack, you're going to form this intermediate here. So you'll have this covalently attached pyruvate, now shown with the alcohol here. And so what you can do now is you have an actual electron sink. Oh, I don't have my stuff here. So now you have an actual electron sink, and you can decarboxylate this and be okay. So you throw these electrons down here, and then you kind of start this electron cascade. It's always kind of fun to do for me. and then I'll go right to that positive charge. So this is going to be right your sink. And then you'll form this species over here. And I had forgotten all my double bonds. All right, I'll put you in there. All right, so now you end up with this intermediate, and so you can just go ahead and pop these out, grab another proton, and then have something that's starting to look like what we were trying to see. And then the last step here really is offloading the moiety here, and then you'll just place these electrons back onto the carbon, reform your ylide, and then you'll form an aldehyde on the way out. So you see that here. And then in this case it's acetaldehyde, and then in yeast or other fermenting species, this acetaldehyde will then undergo a reduction using NADH, seen here. And so NADH is a source of hydride ions, so you'll just throw some electrons in there, kick out this proton to attack. This is similar to NABH4 in your organic chemistry class. And then there you have it. You'll have, at that point, ethanol, and then you'll have restored NAD+, which can go back into glycolysis. So, but once again, the point of this is just to show TPP. So remember, TPP is an ylide. It has this stabilized carbon ion that's going to attack a keto substrate, and then whenever you have that attached, what you've created is an electron sink, and that electron sink will allow you to do things like decarboxylate, and then have a place for those electrons to go instead of them building up charge on just the carbon of the carbonyl. So, and that's what we saw here, right? So you can't just build up charge here. You need to have some place to put those electrons. Alright, so that is decarboxylation of alpha keto acids, but there are other things to decarboxylate too, and the other one is going to be an amino acid. So this is going to use PLP. So I'll do a little more PLP after this, but PLPs are really diverse cofactors. This is just one of the things it can do. And so let's think about if we had an amino acid, just how we did before, how would we decarboxylate it? So here's your amino acid right here. Now I just kind of drew it a different way. And you might be thinking, well, can I just spontaneously decarboxylate an amino acid? And I don't actually have a really good answer for you. I'm sure it can happen, but we use enzymes for this. It doesn't happen very easily, it seems. But you could imagine, you're like, oh, okay, well, maybe I would try and form this CO2 as I do, in other ways. And then these electrons, once again, have to go somewhere. So they're not going to go to this R group over here. So maybe they can go here, and then, I don't know, maybe you form something like that. But this is essentially what PLP is doing. So while I don't know how this reaction would happen spontaneously, this is kind of the concept that we're going to use PLP for, and that's that, once again, you're going to want to have an electron sink to make this possible. Alrighty, so that's really bad handwriting, but anyway. So let's see what that would look like. So this is PLP shown here. So PLP has this nice six-membered ring here with the heterocycle, and this should have a positive charge. And this aromaticity is going to allow this ring to act like an electron sink. And the other really important part of this is going to be this aldehyde on top. And this is going to be where a lot of the magic happens, right? So anything that has an amine can often have a reaction with PLP. And so in this case, we just have a random amino acid. So the amino acid would come over here and form a Schiff base. So this is imine formation. I am not going to do imine formation in your own time. If you want to remember how to do it, you can do so. This is imine formation, also called a Schiff base. Feel free to review your OChem. But for this class, the formation of the Schiff base isn't as important as understanding what's going to happen afterwards. Alright, so once you form a Schiff base, it's going to look like this. So this is the amino acid from, so this is the amine from your amino acid. And now that you have this species here, we are in another similar position as we were before. We now have a big electron sink down here to move electrons to. And so what we can do is decarboxylate. So we'll roll our electrons in, form carbon dioxide. We'll have to break this bond that has to go somewhere. So this nitrogen is looking good. And now that we have this PLP here, there's a place for these electrons to go. So the sink will pull these electrons all the way through and down to the nitrogen at the bottom of the ring. And you'll end up with an intermediate like this. And then what you'll do is you'll reset the aromaticity in the ring. These will all come back up. These will all come back up. And these will come back up. And then you will grab this proton and protonate. And then you have a species right here. Let me draw the, I'm missing my PLP. No. Alright, so then you'll have the species here. And then all you need to do is have water come in and hydrolyze this off. I'm not going to show this, but it's the reverse of Schiff base formation. You're just going to reform the aldehyde and then offload your amine. And you can see that here. Apparently I left this here, but boom, there you go. So you reformed your PLP, and then you formed your amine. So this will be sans carboxylate. So just to review, there's a couple of situations that you're going to have for decarboxylation. You have a beta keto acid. Like I said, they're called beta keto acids because if you start numbering your carboxylic acid, you have an alpha position and a beta position, and your beta position you have a ketone. So it's not really difficult. It's called a beta keto acid literally because there's a ketone at the beta position. And this actually allows a sink to be there, so you have the ability to decarboxylate pretty readily, especially if you have a little bit of heat. Like I said, there's also enzymes that do this, but beta keto acids are pretty easy to decarboxylate. It gets a little more difficult with amino acids and alpha keto acids, so you have these nice cofactors that you'll typically find. So if you have an alpha keto acid, you're going to have TPP that's going to be used, so TPP creates an electron sink. As I said here, if you have a decarboxylation of an alpha keto acid, you have this really unfavorable buildup of negative charge on the carbonyl carbon. So you have to find some way to funnel those electrons somewhere else to make this a stable process, and in doing so you use TPP. So TPP is an ylide stabilized carbanion that allows you to basically have this nice aromatic ring to suck electrons into to make a otherwise unfavorable process favorable. And then in the other case, the third case here, you have amino acid decarboxylation, which uses PLP. And so PLP will do a similar function where decarboxylating an amino acid isn't a very favorable process, but you could imagine if you had a place to move those electrons, like a sink, then you would be able to do this type of reaction. And then in the case of biology, a lot of enzymes use PLP to perform this function. And so, and that's what we just ran through there. Once again, it's similar. PLP will allow you to do this decarboxylation step and then just suck all those electrons down into the ring. That's kind of the basics for decarboxylation. So since we touched on PLP, I think PLP is a pretty difficult cofactor to get your hands on. You guys got to really just do the reactions a couple times. And so I will do a little brief overview on PLP, but I would recommend that you become familiar with PLP. It does a lot of interesting stuff, and if you are comfortable with the cofactor, then a lot of questions that might be difficult will not be so difficult anymore. Alright, so we have, in this case, here's a list of things that PLP can do. So like I said, it's a useful cofactor. It can do transamination reactions, which is what I will show you in just a second. It can do isomerization reactions, which I'll also show you. It can do decarboxylation reactions, which you just saw. It can also do some interesting beta elimination reactions. This is specifically true in amino acid degradation, but we won't go over that today. If you're interested in that, let me know and I can send you something. Alrighty, so we're just going to start kind of where we were last time. So this is once again PLP. It's an electron sink. And the first step is the shift base formation or imine formation, whatever makes you happy. And so once you form your shift base or your imine, it looks something like this. And this actually has a name. It's called an aldimine. And so I actually like to think of PLP through the steps of the different named states it can exist in. So this is called an aldimine because you can see here, if you put an H, it kind of looks like an aldehyde, right? So an aldimine, so here's an aldehyde. Right, so this is an aldehyde. And then if you have, in this case, the nitrogen equivalent, it's an aldimine. Cool. So it's called the aldimine form because you have an aldimine at this position. Let's move this out of the way. Come on. All right, so when you have the aldimine form, this is really where you can begin to do a bunch of different stuff. So the aldimine is where we saw the decarboxylation last time. So that's when you can either lose CO2. It's also a time when you can lose this proton, and I'll come back and do that in a second, and that'll allow you to actually do an isomerization reaction. But for transamination reactions, which is what we're doing here, we're going to remove the amino group of this amino acid. So we have to do a couple more steps. So we go to the aldimine. And when you have the aldimine, what you're going to do next is you're going to deprotonate. This proton, flow some electrons in here. You just do the cascade. It's a lot of fun. Whee! All right, so once you do that, you're going to have this intermediate. There it is. Okay, so you'll have this intermediate here. All right, and then what you're going to do at this point is you're going to reset your ring and reprotonate, and then you're going to form what's called the ketamine form of PLP. So let's go ahead. This is going to come off. It's going to grab a proton. And then you'll have the ketamine. So the ketamine is called a ketamine because, if you can imagine, you have a ketone, all right, and then in this case you have the nitrogen equivalent of that. Ketamine. All right, so you have the ketamine form here, and the reason that you've done this is because now you can actually take off this top part and you're going to leave behind the amine. So this gets left behind, not the book series, just the amine. All right. So the way that happens is H2O is just going to come in and just going to be the reverse of the shift base formation or the imine formation, right? You'll attack here, sorry. Right, so you'll attack there, you'll go through a bunch of deprotonation and reprotonation events, and then you'll end up at pyridoxamine. So here we go. This is pyridoxamine. It's called pyridoxamine because it has an amine here, right? Look at that. It's got an amine, so it's called pyridoxamine. All right, and then you'll also form your alpha keto acid. So now you have deaminated an amino acid, and what that gives you is an alpha keto acid. All right, so and this is the way a lot of these aminotransferases work. You'll have a certain amino acid that drops off the amine, and then it'll be specific for what it transfers it to afterwards. That's the way that a lot of your amino acid metabolism works. And for natural products, we talk about secondary metabolism, which is specialized metabolism, and similar reactions are going to happen here too. So if you are familiar with your PLP stuff from biochemistry, then you'll be in a good position. All right, so once you have the pyridoxamine, you'll have the acceptor come in. So this is maybe another molecule. So I drew another just random alpha keto acid. There is no rhyme or reason to this. This is an alpha keto acid. All right, but anything with a carbonyl that can be turned into an amine can come in. And so once again, you're going to have the alpha keto acid come in, and you're going to reform a shift base, or you're going to actually reform your ketamine. So this will come in and attack, and then you'll be right back to where you were. And so this is why I like to name stuff and think about where I am, because you'll see I go from aldamine. Yeah, I'm going to make that white. Go from aldamine here, then I go to ketamine, then I go to pyridoxamine, then I go back to ketamine. So it's going to be, you go back from where you came. All right, so once you have the ketamine, you're getting close. Now you actually have to go back to the aldamine form. So in order to do that, you have to do a deprotonation of these protons that are close by. So you deprotonate from this position. These will come down into the ring, so you do your cascade. Looks like that. Once again, you'll be back at this intermediate here, and then you can reset the aromaticity in the ring, and in doing so, you're going to switch it to the aldamine. Look at that. It's all conjugated all the way to the top, and then over here, we'll grab this well-placed proton. Nice. All right, so once you do that, you'll have something that looks like this. This is going to be your aldamine, and then you're pretty much done. So aldamine here. Let's go back to that color. Okay, cool. So you have aldamine here. So the last thing to do is really just hydrolyze off this imine here. Right, so that's going to be, of course, a couple of deprotonation and reprotonation events, which I will spare you. So that will offload, in this case, your very new amino acid, nice and shiny. And then you'll reform your PLP. All right, so that's basically how you'll do transaminations. And just to go over it, because I know it's quite a bit, you have PLP in either the aldehyde form, and you might have heard the internal amine, external amine stuff. If you don't know what that means, don't worry about it. Mike doesn't really go too much into internal amine and external amine, but those are terms used for whether the PLP is attached to the active site enzyme or not. And typically, if it's a PLP-dependent enzyme, the enzyme will have a lysine residue that will actually form an imine or a shift base with PLP, and then when the substrate comes in, it'll actually switch, and then it'll form an amine with the substrate. But in this case, you can just start with the aldehyde. If you don't know what anything that I just said means, don't worry about it. You just have the aldehyde, and the first step is going to be shift base formation or imine formation to give you your aldamine. All right, so once again, you have your aldamine, and that's a good place to be as an intermediate, and I'll show you in just a second. But if you have your aldimine, you can deprotonate, you can do a bunch of stuff here. In this case, for transamination, what we need to do is switch from the aldimine to the ketamine so that we can leave behind this amine group, right? So in order to do that, you have a base that deprotonates. These electrons will flow down into the ring. You'll form an intermediate here. Then you'll reset the aromaticity in that ring, and in doing so, you'll protonate at this position. And then now you've effectively moved your aldimine into a ketamine. So you're taking the double bond from this position, and then you're going to move it to this position. And so once you have the ketamine, then you can hydrolyze it off with water, and then you'll form pyridoxamine, which is the intermediate that holds the amine group, and this allows the next substrate to come in and be the acceptor for this amine. So in this case, I just have an alpha keto acid coming in, and it's going to reform a shift base, and in this form is once again going to be a ketamine. So we're going back from where we came. Aldimine, ketamine, pyridoxamine, ketamine, and then yes, we have to deprotonate at this position here to reform this intermediate, which then allows us to push the electrons back into the aldimine form. And then once you have the aldimine form, you can offload whatever is now going to get an amine, right? So since we've switched it, that means when water attacks, that'll attack here instead of here, and then you'll offload your new amino acid and then reform PLP. So as I said, I mentioned that there's a special place at which you can consider lots of different positions or lots of different reactions that you can do. Go ahead and delete this guy. And that's really at this aldimine position. So this is the same place where we decarboxylated. Or you can decarb, right? So in that case, you would have, let's see if I can erase. Right, so that's what we did last time. Basically, when we were in the aldimine form, we were able to use this sink to remove this carboxyl group, right? And then what we did previously, just a second ago, was we were actually able to use this position to remove this proton, right? And so if you use that position for either one, like I said, you can decarboxylate it. But you can also do an interesting isomerization. And in this case, if we do the proton route, so if we're going this way, we deprotonate, we form this intermediate here. Hang on, this intermediate here. Now, when we come through, and I'll just go ahead and redraw it. Let's just do it that way. I don't want to confuse too many people. So this is if we deprotonate. We're going to do this for isomerization this time. Let me go ahead and get rid of these arrows. Alrighty, so if we're at the same position here, so once again we grab this, we're grabbing this proton here, alright, and so you're going to end up here. Now, instead of forming the aldimine, what we'll do is we're just going to go ahead and reprotonate. And so by reprotonating, we can actually change the stereochemistry. So if we reprotonate from the opposite face, so over here you have an L amino acid, right? So this is an L amino acid. down here. So if we redraw that, now we'll have a D amino acid. So what you've been able to see is that there's a couple different ways you can go with these things, right? So as I said before, we decarboxylated it, and that's what we did last time. I'm not going to draw it for you, we just did it. But anyway, you can decarboxylate and go that way. You can also deprotonate it and then reprotonate it from the opposite face and come this way and form a D amino acid. And then if you have that D amino acid, since you're still in the aldimine form, just have H2O come in and knock it off. And then you'll reform your PLP, and then you'll have your D amino acid. Alright, well I think that about covers it. So just to review quickly, PLP is a useful cofactor. It can do transamination reactions, which is what we just went over. It can do isomerization reactions we just touched as well, and then decarboxylation reactions. And then it can do beta eliminations too, which I'm not showing you today, but you guys can go look it up if you're interested. Otherwise, I would definitely recommend being familiar with PLP. It's an interesting cofactor. It should come up again when we talk about the shikimate pathway and some other situations as well. So hopefully you'll find this helpful. Otherwise, thanks, and I hope you guys do well in your upcoming exams.